Hi everyone! In today's video, we will introduce neural networks and explain how they work. I'll start with a very simple concrete example and walk you through each step in detail while making the network more and more complex. So let's get into how neural networks learn. In general, in machine learning, we aim to make informed decisions. This means we want to look at some data that we have gathered and make some assumptions or predictions for future cases based on this past data. More formally, for almost every machine learning algorithm, we always have data typically denoted as X. We then want to use that data to get so-called predictions, denoted as Y hat. A prediction is essentially an educated guess about the output or outcome based on the input data. To arrive at this prediction, we need a mechanism that, based on the input data, comes up with the prediction Y. This mechanism is usually called the model, here denoted as M. To further understand this concept, let's look at a simple example. Imagine we work at a big real estate firm and we have received hundreds of house evaluations every day. At some point, we get tired of evaluating each house individually. We think we should automate this process. As we have evaluated thousands of houses before, we have access to a lot of data on houses and their respective prices. Let's assume for simplicity that we only need to look at the number of floors and the total area of property to evaluate the housing price. Here the number of floors and total area of property will be given by the data X. This is given by our model in form of a vector. Each dimension of that vector corresponds to certain information. Here the first dimension is the number of floors and the second is the total area of the property. These two categories that need to provide the necessary information to create an informed decision are also called features in the machine learning domain. In machine learning, we are always interested in how the input correlates with the predicted variable, as we want to find the relationship between these two types of variables. Just a side note, once we decide an order of these features, we cannot change it anymore, as the model expects the input to be in this order. We can then feed the vector into our model that somehow transforms the input data into the predicted value Y hat. In our example, the predicted value of our model is the housing price itself. So the goal here is to find the model M that, based on the number of floors and total area of the property, finds the corresponding market value of the house. Let's remove the second feature, the area of the property, to make it even simpler and possible to visualize as a 2D plot. So let's plot the data, where the x-axis is the number of floors and the y-axis is the property market value. Again, our task is to find the market value based on the number of floors. The simplest solution of solving this task is to find a line that best fits this relationship. A line can be described by its slope and the y-intercept, so mathematically it's represented as y equals ax plus b. To make things more consistent with the naming scheme in deep learning, we change the slope a to w for weight and the y-intercept to b for bias. This line always yields the market price given the input. So for every number of floors, I can complete the market price automatically using this formula. Here w and b are called parameters, as we can change them to create different models. The main question now is, what are the best values for w and b to best predict the market value given the number of floors? While there is an analytical solution to this using linear regression, I purposefully won't get into this as this video is about neural networks, and I want to keep it as simple as possible. Instead, let's analyze what happens if we change w and b. If w is 0, we will always get b for the market value, meaning the number of floors has no influence on the market value itself. If we increase w, we imply that the number of floors is proportional to the market value. Here the absolute value shows the impact on how much more expensive the price gets if we increase the number of floors. If we set w to a negative number, we imply that the market value goes down with an increasing number of floors. So the main question is, what is the best model, aka what are the best parameters to have a line that will tell us the most accurate market values? But before we get into solving this question, I want to talk about a major assumption in deep learning. The assumption is that we can make predictions in the future based on the data that we have already seen. Meaning based on the houses we have seen, which all have a number of floors and a market price, we can predict the market price for future houses. Here I represent the future unseen data as blue dots and the seen data as white dots. We can see that the blue points follow the trend of the wide and known data. Thus, if we find the best parameters for our current data, we will be able to generalize these solutions for future data. Now we can compute the best model for the current data by minimizing the distance between the data points and the function. We can clearly see that the line is getting worse when the distance to the wide data samples are getting larger. Note, this type of learning is called supervised learning because we use data that already contains the variable that we are looking for, the market price. This value is also known as the label for each data sample. So the supervision is the label for each data sample. For the majority of cases, deep learning is always supervised. This means that to train a neural network, we always need the corresponding label. And just for completion, there are neural architectures like autoencoders that fall under self-supervision, but we won't get into the details here. Generally speaking, our prediction tool can be separated into two steps. First, we need to look into the data that we already have. This is called training. We then choose the best parameters to create the best model based on our training data. Once this is done, we can use that model in the prediction or inference phase on unseen new data. The example I showed is very simple, and most use cases in the real world don't have linear dependencies. For example, how would you find the best model if the relationship between input and output is best described as this function? Okay, so what is training and what actually are neural networks? All in all, neural networks are very complex function approximators. So training is finding the right parameters to approximate the true underlying function that most of the time cannot be analytically described, meaning we don't know the exact formula of a function. In this case, we only have two parameters, w and b, to approximate a linear function. But as we said, we need to be able to approximate more complex functions. So how can we increase the complexity of our model to represent such data? One idea would be to increase the number of parameters that we can choose. We can nest them such that the output of the first computation is the input of the second function. We can add w2 and b2 to compute the second part of our model. Now the model has four parameters. The output of the first computation, w1 times x1 plus b1, will be multiplied by w2 and then added to b2. This nesting is what neural networks do, and each individual setting is called a layer, but more on this later. If we now analyze our function in the plot, we still see a line. Thus adding more layers didn't add more complexity or expressiveness to the model. This is because we are still only doing linear operations. To change that, we can wrap the output of one layer with a nonlinear function. This will result in non-linearity and adds more complexity to the model. Such a function is called an activation function, and there are many different types of activation functions. To find the best one can be challenging and is often found by trial and error. In general, every differentiable function can be used, but it has to be carefully chosen to not affect the model in a bad way. Before exploring more ways in adding complexity, I want to introduce the most famous activation function, or nonlinearity, called ReLU. ReLU is 0 for all negative input, and the input itself for the rest. We can then add the same nested structure to the ReLU function, as we did before with the quadratic function. And again we see that changing the parameters just leads to different versions of the ReLU function, with shifts or variations of slopes. Also nesting it, even multiple times, results again in a ReLU function. Let's assume we want to approximate the function f of x equals x cubed. To approximate this function, we want a negative slope for the negative values and a positive slope for the positive values. Additionally, we want the flat graph around the origin, so we can divide the x-axis into three areas. For each area, we choose parameters for the ReLU function such that the output fulfills the condition. As we have the same function for both ranges from negative 0.5 to 0.5 and from 0.5 to infinity, we can combine them. Now to get the final function that represents the entire x range, we can simply add both results. When plotting x cubed into the same plot, we can see that the overall trend is correct, but we still need to fine-tune the slopes of the ReLU function to allow for a steeper increase. And voila, we approximated x cubed with only two ReLU functions. In fact, we have already trained our first model by handpicking the right parameters. As you can tell, this model is imperfect, as the f-cubed graph does not always touch our approximation. We can check on how good our model is by finding the distance of data points on our approximation and true function. By summing them up, we get a scalar that corresponds to the approximation error. But as we can see, some values are positive and some are negative, so the error can be smaller as these terms cancel each other out. To overcome this, we can simply square each term and then perform the sum. We then still need to divide by the number of samples that contribute to our error to make it invariant to the number of samples. In general, we call this error the mean squared error, or MSE, which is the average squared distance of the approximated and learned function to the true function. Here the predicted value is y hat and the true value is y. P is the set of all tuples of predicted and true values. Let's look again into our handcrafted model. It consisted of 6 parameters. Instead of this mathematical formula, we can visualize the function using a network architecture. Here the input is x1. We denote the multiplication of the weight w1 as the connection to the first part of the equation n1. N stands for neuron, as neural networks are based on how our brain works. So n1 is the output of the ReLU. Note that also the bias is added to the product. We can then also compute the second part of the equation by adding a connection using the second weight w2 from the input x1 to neuron 2. When multiplying the whole equation with 2 more weights, we arrive at our final prediction variable y hat. Note that there is again a bias. Looking back, we have formally learned how neural networks take input and transform them into the desired output value. This is called the forward pass and is necessary to arrive at a prediction. This transforms the input to the output value based on its weights and biases. Let's see such forward pass in action. Before we start, we need to assign values to every weight and bias. This is the initialization of the network. After initializing the network, we are ready to take the first input. Let's say x1 is 5. Multiplied by w1, or 0.5, is equal to 2.5. We then add the bias, which yields 3.5. As this is a positive number, it is unaffected by the ReLU. Thus, n1 is equal to 3.5. We do the same computation with weight 2, and are then able to compute the final output value w hat by adding the multiplication of n1 with w3 and n2 with w4. This is our first simple structure of a neural network. Given some one-dimensional input and an initialization, it can transform the input into a one-dimensional output. If we look again into the setup from the beginning, we want to give a black box, our model M, the input data that is necessary to make an informed decision and then get the output value that we want. This is exactly what we did. Given some input x, let's say it's 0.1, or the normalized number of floors, we can transform it into our desired output y, the market value in 100,000 euros. As our model grows in complexity, we can add the second feature, the area of the property. We can also increase the number of parameters and layers. The number of parameters, layers, and functions of a model is called the model's architecture. It is often chosen again by trial and error, as finding the right architecture is not a trivial task and needs to be chosen to best fit the task. We now have 2 input dimensions for our model, as we have 2 features. Let's look at the first input dimension x1. This is connected to every neuron in the second layer. However, n1 is also connected to the second input dimension, the area of the property. So we compute the product of w1 and x1, as well as the product of w3 and x2 to compute n1. Similarly for n2. This example shows how to get the predicted value, but this value is random as we initialize the model randomly. It has nothing to do with our predicted value yet. How can we guide the model into changing the parameters in such a way that the prediction of the model is closer to what we actually have in our data? If we think of how we learn, we usually look at the problem, try to solve it, and then look at the solution. Now we compare the true solution with ours and make adjustments to our calculations such that we arrive at the true solution. We can do something similar for deep learning. We can take the solution of our model and define an error function. This error function is usually referred to as the loss function. It basically is the difference between the actual value y and the predicted value y hat. As our example is simply the one data sample, we can simplify the function to the following. Here one usually uses the L2 distance, which is the squared distance. But one can also use the L1 distance or the absolute difference. One can potentially use every distance that is differentiable. So to get an accurate prediction, this error measurement needs to be small, aka we want to find the best suiting y hat given the loss function. This alone doesn't help us yet, as we don't know how to change the weights and biases of our network to predict the right y hat. But here's where the coolest thing happens, the main reason why deep learning works. As we have discussed before, we can rewrite the prediction y hat in terms of every input and parameter, essentially the forward pass. We now can formulate the task in the perspective of the parameters, which is helpful as we want to change them. The parameters should transform the input in such a way that y hat is equal to y. We can now propagate the argmin of y hat to every parameter and find the parameters of our function that minimize the loss. To minimize a function, we usually take the derivative. I will visualize this in a second, but to clarify the notation, the delta over delta y hat is called the partial derivative. Partial, as the MSE has two variables that we could derive after, y hat and y. We are only interested in deriving with respect to one variable, y hat. This is indicated by the fraction. But why do you derive a function to find its minimum? The MSE is essentially a quadratic function. The x-axis is essentially y hat, and the y-axis the value of the loss. Let's look at its derivative 2x. When we evaluate the derivative on the origin, we notice that the derivative is also 0. In fact, for all differentiable functions, the derivative is 0 if the underlying function has either a saddle point, maxima, or minima at that position. To show this, let's plot a random polynomial and its derivative. Again, for all extremas, the derivative is 0. So when deriving the MSE and setting it to 0, we can find the position where we know an extrema is located. So with that in the back of our mind, how can we proceed in our loss function, where we have more than just one parameter? In general, we want to derive this formula with respect to every parameter there is, so every weight and every bias. To visualize the next mathematical steps, let's assume that we only derive for two weights, W1 and W2. The rest is left constant. We can then plot the MSE in a three-dimensional graph as W1 and W2, and on the third axis is the loss itself. Imagine that the loss is described by this function. The closer the loss to 0, the better, as that means that we don't have an error. The larger the function, the worse the approximation. So in theory, we want to find the minimas of this function, here indicated by the yellow dots, as these yield the best parameters W1 and W2 that minimize the loss. So every point in this graph represents a tuple of W1 and W2 and its corresponding performance in the error. In reality, we don't know the best choices for W1 and W2, but we can randomly choose them and evaluate them. So let's say we choose this point and initialize W1 and W2 respectively. Our goal is now to move the dot towards the minima, or to change W1 and W2 slightly such that we move towards the minimum. The path is here indicated as white. Again, let's look at this in a 2D perspective. Only taking one weight into account, we would derive the function and find the minimum by looking at where the derivative is 0. In the 3D setting, we do something similar. We also need to derive the function, but with respect to both parameters, as we want to improve both of them. When we write this as a vector, it will yield the direction of steepest ascent, meaning where does the graph go up the most. We can easily flip the vector by adding a negative sign, and voila, the resulting vector points in the direction of steepest descent, or where the graph curves down the most. We can then follow these vectors and arrive at a minimum. So we need to evaluate the function at this point, compute the derivative, and find the direction on how to change the weights to obtain a smaller error. Then we update the weights with the vector, which yields us the next point. We repeat these steps to hopefully converge to a minima. What we have seen here for two parameters needs to be done for every parameter in our model simultaneously. We compute the derivative of the loss with respect to the parameter in question, we can write this as the following derivatives. Then, when using a vector describing all the derivatives in each dimension, we've obtained the so-called gradient. With that, we can now update the weights to yield a better prediction y hat. We first compute the forward pass with randomly initialized weights w and b. In machine learning, we usually summarize all of them using theta. Then we compute the gradient. The new parameter is the old parameter plus a small step following the negative gradient. Alpha, or the small step, is called the step size or learning rate. It dictates how far one should go down in the steepest direction. This hyperparameter needs to be carefully chosen, as many small steps lead to longer conversion times and therefore training times. Larger steps can overshoot the minimum and lead to bad model performance. So with all of this, we have the entire recipe of training a neural network. We first initialize the network at random, meaning for every weight and bias we choose a random variable. In research, different methods exist that cleverly initialize the network to yield better results. We then compute the forward pass, where we transform the input variable into the predicted variable. Then the loss function is computed, which is typically the MSE. But different tasks can actually lead to very different losses. They can be highly complex to force the model to have certain properties. After computing the loss, we compute the gradient of the loss. It is a vector pointing in the direction of the steepest ascent. Finally, we update the weights according to the negative gradient, the amount of changes indicated by the learning rate alpha. We then repeat steps 2 to 5 over and over again and iteratively find a local minima. So far, we've only discussed how neural networks process a single data sample. However, in practice, multiple data samples are typically sent through the network in parallel. This approach not only speeds up computation, but also helps extract common patterns in the data rather than focusing on individual properties. By learning common patterns, the model is better equipped to handle unseen data, as these patterns are more likely to be presented in new data samples than specific individual properties. To process multiple data samples at once, the data is split into so-called batches. Each batch is sent through the model individually. The gradient is computed for every sample of the batch and averaged across it. This average is then used to update the model. Once all batches in the dataset are processed, one epoch has finished. Typically, models are trained multiple epochs to achieve the desired performance. And voila, this is how the simplest form of neural networks learn. Of course, there is much more into it, like splitting the data into train, evaluation and testing, overfitting or underfitting, and much more. But I want to keep this video as simple as possible and might do individual videos later on these topics. Thank you so much for listening to my video. I hope you found it helpful and understand now how neural networks work and what learning is.